In the previous lesson, we covered time division multiplexing, where channels share a line by taking turns in time. Now let us look at the other fundamental approach, frequency division multiplexing, or FDM. In FDM, each signal is modulated onto a different carrier frequency. All the modulated signals are then combined and transmitted simultaneously over the same medium. To prevent interference between adjacent channels, unused frequency gaps called guard bands are placed between them. At the receiving end, bandpass filters separate the individual signals, and each is demodulated to recover the original data. A classic example is analog television broadcasting, where each TV channel occupies a 6 MHz band separated by guard bands. FDM is also the basis of how full duplex modems work on a telephone line. The 300 to 3400 Hz voice band is split into a forward channel from 500 to 1800 Hz and a reverse channel from 2000 to 3300 Hz. While TDM divides time into slots, FDM divides frequency into bands. Both are still widely used today. Standard TDM has a limitation. If a terminal is idle, its time slot is wasted. Statistical time division multiplexing, or STDM, solves this by dynamically allocating time slots only to terminals that have data to send. This makes bandwidth usage much more efficient, allowing STDM to carry 2 to 5 times more traffic than regular TDM. STDM can even have more terminals than available time slots. When all slots are busy, excess data goes into a buffer. If the buffer fills up, data can be lost, so traffic analysis is essential. STDM forms the basis of modern packet switching technologies like IP, frame relay, and ATM. Two other multiplexer types are worth mentioning. Intelligent multiplexers, also called concentrators, combine many low-speed lines onto a single high-speed link. Digital loop carriers are a common example, connecting telephone subscribers to the local exchange. Inverse multiplexers do the opposite. They split a single high-speed data stream across multiple lower-speed links, like separate T1 or E1 lines, and recombine them at the far end. This is useful for applications like video conferencing that need high bandwidth but only occasionally. Wavelength division multiplexing, or WDM, takes multiplexing into the optical domain. Instead of dividing time or frequency, WDM puts multiple signals on a single optical fiber, each carried on its own separate wavelength of light. Dense WDM, or DWDM, spaces wavelengths very closely together, at intervals as small as 0.4 or 0.8 nanometers near 1550 nanometers. Modern DWDM systems can multiplex 160 or more wavelengths onto a single fiber. Each wavelength typically carries a TDM signal at 2.5 or 10 gigabits per second. With 160 channels at 10 gigabits per second each, a single fiber can carry 1.6 terabits per second. The ITU, the International Telecommunications Union, has standardized a frequency grid with 100 GHz spacing, centered around the C-band from 1530 to 1570 nanometers. The L-band from 1570 to 1610 nanometers and S-band from 1490 to 1530 nanometers provide additional capacity. A critical component is the EDFA, the erbium-doped fiber amplifier, which amplifies all wavelengths simultaneously without converting to electrical signals. DWDM is the backbone of today's Internet, carrying the vast majority of intercontinental and long-haul data traffic. Let us work through an example that shows the power of DWDM. Imagine a digital library containing 10 million books. Assume each book is about 40,000 bytes or 320,000 bits. The total data is 10 million times 320,000 bits, which equals 3.2 terabits. How long would it take to download this entire library? With a 56 kilobits per second dial-up modem, the time is 3.2 times 10 to the 12 divided by 56,000, which equals about 57 million seconds, or approximately 1.81 years. With a VDSL connection at 52 megabits per second, it would take about 61,500 seconds, or roughly 17 hours. But with a DWDM system using 100 channels at 10 gigabits per second each, the total throughput is 1 terabit per second. The download time becomes 3.2 terabits divided by 1 terabit per second, which equals just 3.2 seconds. That is the difference between nearly 2 years and 3 seconds, demonstrating why DWDM is essential for modern backbone networks. Let us review. FDM, frequency division multiplexing, assigns each signal a different carrier frequency with guard bands preventing interference. STDM, statistical time division multiplexing, dynamically allocates slots for 2 to 5 times the efficiency of regular TDM and forms the basis of IP and packet switching. Intelligent multiplexers concentrate many low-speed lines onto one high-speed link. Inverse multiplexers split a high-speed stream across multiple low-speed links. WDM and DWDM multiplex up to 160+ wavelengths onto a single fiber, with each channel carrying gigabits per second, amplified by EDFA without electrical conversion. DWDM is the backbone technology of today's Internet. In the next lesson, we will explore wire transmission media, twisted pair cables, DSL technologies, and coaxial cable.